A couple of videos ago, we saw that evaluating a trace at a Cauchy-Johnlistic basis element was the same as evaluating an immanent at a totally non-negative matrix. Let's look closely at when that's the case. So let's let W mu be the longest element in the Young subgroup S mu. So that is W mu equals a reversal S1 lambda 1 times a reversal S lambda 1 plus 1 to lambda 1 plus lambda 2, etc. Let's let d mu be this star network where we have stars of size mu1, mu2 up to mu r, that is mu1 spokes on each side, mu2 spokes on each side, etc. And let's let A mu be its path matrix. So this is going to consist of blocks of ones. And zeros everywhere else. Then for all traces of the symmetric group, we have theta of C sub W mu equal the evaluation of the theta immanent at A mu. Now these are not the only planar networks and path matrices and elements of the symmetric group algebra that have this property. There are some more planar networks and their path matrices that allow us to write this inequality, and they involve bijective skeletons. So recall that a bijective skeleton is a multi-set of edges. Well, let's say it's a planar network that can be covered by a path family. And we can assume that this path family has type E. Some edges might be covered twice or more. So for example, here's one bijective skeleton. You can imagine two paths going across this, and I mean they could end up being type S1 or they could end up being type E, but we can just assume they're type E, because if we can cover this with a path family of type W, we certainly can cover it with a path family of type E just by requiring that paths never cross. We can cover this with two different path families of type E, in fact. And this planar network is another bijective skeleton because we can imagine two paths crossing this. There's only one way to do it, and those two paths are going to share these two edges between the three vertices there. Now I claim that if, let's say K is a bijective skeleton, of order n, so n sources on the left and n sinks on the right. In which there are no two vertices let's say x1 and x2. This could be sources, sinks, or intermediate vertices. There are no two vertices with more than one path from x1 to x2. And then we can conclude two things. For all permutations W and Sn, there is at most one path family of type W covering K. And two, there's no proper subnetwork of K which is a bijective skeleton. So I guess we could say that K is a minimal bijective skeleton. This bijective skeleton here is not minimal. We can see that this one is inside of it and it's also a bijective skeleton. But this bijective skeleton doesn't have the property that from any vertex to any other vertex there's at most one path, because there's two paths from this vertex to that vertex. The proofs of these two statements are essentially the same. So let's assume there are two path families of type W. Covering K. If they're different path families, then there's some path that's different when we compare them. That means that for some I, let's call the two path families pi and sigma. So for some I, we have that the ith path of pi is not the same as the ith path of sigma. Otherwise they'd be the same path family. But then there are two different paths from source I to sink Wi. Contradicting the fact that this bijective skeleton has the property that there are never two different paths from one vertex to another vertex. And to prove number 2, I'll just write it here. Let's assume that there's a proper subnetwork L of K, which is a bijective skeleton. Now let's look at the two path families of type E covering these. Let's let pi and sigma be the two path families of type E covering these. Now, since they don't cover the same bijective skeleton, then they can't be exactly the same. So these must be different. And that means for some I, we have pi I not equal to sigma I. But then again, there's two different paths from source I to sink I. So that's all there is to it. All right, so let's call these minimal bijective skeletons because of this property number 2. Now I claim, let's say K is a minimal bijective skeleton. Then recall that zk is the sum of type of pi over all path families of pi that cover K. So it turns out that has to be a Kaiser-John-Lustig basis element CW for some W and Sn. So we know that Z of K has the form P times a product of Kaiser-John-Lustig basis elements indexed by reversals. Oops, I'm sorry, this should be 1 here. We're not doing anything with Q's. So this sum equals a rational number times a product of Kaiser-John-Lustig basis elements indexed by reversals. for some intervals I1, J1 through IR, JR, and some rational number P. P is 1 over a bunch of factorials that come from stars that, oh, actually this is a minimal bijective skeleton, so that's not going to happen. Okay, we do need the P because when we multiply these Cauchy-Listic basis elements together, they very well might lead to these regions, and our minimal bijective skeleton might be obtained from this by combining two different paths that go between vertices into one. And so this product is going to be for the original planar network, and then when we get rid of double paths, we're going to be essentially dividing by 2 or dividing by 6 or dividing by something factorial each time we collapse certain edges. So this is correct. All right, now by Springer's result, on products of Cauchy-Listic basis elements, so this has to be a non-negative linear combination of Cauchy-Listic basis elements. Now the product alone belongs to this span. I guess if we divide by an integer, then what we really have are non-negative rational numbers here. I'm just going to say divided by, these are going to be non-negative integers. Well, okay, I'll say span so the coefficients are all going to be rational numbers which are greater than or equal to 0. Now if two different permutations W appear in this expansion with non-zero coefficient, then they both appear with integer coefficients. Let's say W and V appear with non-zero coefficients, and I really mean C sub W and C sub V. Then these coefficients of CW and CV must both be integers. Because W is appearing because of the number of path families of type W covering K. That has to be an integer. And maybe V is greater than W, so you might think that the coefficient of W here, half of it, plus the coefficient of W here, half of it, add up to an integer. But then what about the greatest element in this Cauchy-Listic basis element? That's V, and that's its coefficient is going to tell us the number of path families of type V here, so that's got to be an integer there also. They must both be integers. Now this is a sum of all permutations less than or equal to W, and this is a sum of permutations less than or equal to V. So those coefficients, let's say A and B, let's say they're A and B. And they're both non-negative integers. But then the identity element E inside of both of these appears with coefficient A plus B. And that means there are A plus B path families of type E covering K, and that's a contradiction. We know that there's exactly one path family of type E covering K. So this minimal bijective skeleton has to satisfy Z of the minimal bijective skeleton equals one Cauchy-Johnson basis element. Now let's recall Stembridge's formula for evaluating imminence. So if A is the path matrix of a planar network D, I'll just write that below. Then we can evaluate the theta imminent of it by taking the sum over all bijective skeletons in D, the weight of that skeleton times the sum of the types of path families covering K. Now, if D is a minimal bijective skeleton, then this is theta imminent of A equals, we don't need to sum over all bijective skeletons because there's only one of them, D itself. And if this is an unweighted minimal bijective skeleton, then this weight is just 1, and then the imminent is just Z of K, which we know is a Cauchy-Johnson basis element. So just like what happened with our maximal elements, our maximum length elements of Young subgroups, we have this planar network and then a matrix, a black diagonal matrix of submatrices of 1s, 0s everywhere else. We can take the theta imminent of this matrix to evaluate theta at the Cauchy-Johnson basis element corresponding to this planar network. So it turns out, well, this certainly is a minimal bijective skeleton because there's no vertex here, no pair of vertices where we can find more than one path from one vertex to the other. So this is part of a larger class. If we look at all minimal bijective skeletons, then we have the same property. We can evaluate the imminent at the path matrix. The theta imminent corresponds to evaluating, this should be theta of z of k, or theta of some Kaiser-John-Lustig basis element. So now the question is, for which permutations W can we do this? Which permutations are going to end up there? Not all of them. So for which permutations in Sn is there a minimal bijective skeleton D such that theta of the Kaiser-John-Lustig basis element indexed by W equals, well, I guess I don't really need theta. When is this Kaiser-John-Lustig basis element indexed by W equal to Z of D? When is there a minimal bijective skeleton D such that the Kaiser-John-Lustig basis element equals Z of that bijective skeleton? Because then for A equal to the path matrix of D, theta of the Kaiser-John-Lustig basis element equals the theta immanent of A. And the answer is when W avoids the patterns 3, 4, 1, 2 and 4, 2, 3, 1. And we're going to look at that more closely in another video. The end.